Okay, so chapter 29. Okay, so all right. So chapter 29.1, we'll be dealing with magnetic fields and forces. So let's say we have a bar magnet. We know that electric fields surround a charge. So magnetic fields surround magnets and moving charges. So the magnetic field is going to go from the north to the south pole. And you can have many different magnetic field lines, whatever, kind of the same configuration as, electric charge. End on north pole, or start on north pole, end on south pole. Similar configuration, we have electric fields from one positive point charge, and they all end on the negative. So it's similar, but not the same. So as we have here, we understand that electric fields surround electric charges. We know that already. Magnetic fields, and the symbol for the magnetic field is, we're going to use B. Surround charges that produce magnetic forces, and we'll see that in a moment, because the magnetic force we're going to see is perpendicular to the speed of the charge and the magnetic field through which this charge moves through. If a charge is not moving, there's not going to be any magnetic. Magnetic field produced. 1 second. So we're going to see when we get to Faraday's law that we need a moving charge to create a changing magnetic field, and vice versa. If we have a changing magnetic field, then we can produce an electric field. So a static charge, as we saw back in electrostatics, chapters 23, 24, etc., when the charges are not moving, we're not going to get any magnetic fields produced. So not only will a moving charge produce its own magnetic field, or you can have a magnetic field and already produced and have the charge move through. In either case, we're going to get a magnetic force that's perpendicular to both the field and the charge. So before we get to all that, we're going to have magnetic fields that surround charges, moving charges, and those moving charges will produce magnetic forces. And we also know that magnetic fields surround magnets, magnetic substances. Such as your magnets. So pretty simple, typical, just baseline. Now I'm talking about this magnetic force. We're going to denote the magnetic force with this symbol FB, where B is magnetic field and F the magnetic force produced by this, the magnetic force produced by a moving charge in a field, magnetic field. So this is going to be symbol for magnetic force. B is magnetic field. So experimentally, it's been shown that if we have a charge move through a magnetic field, and these X's are going to denote a magnetic field that's going into this board. So when you see something like this, I think we saw something like that in previous chapters. This would be the magnetic field is going into the board. And if you see a dot, it's like an arrowhead, the magnetic field is coming out of the page. So in this case, the magnetic field is going into the page. And let's see that we have a charged particle moving with a velocity v. Well, in order to figure out where the magnetic force will be pointing, we have to use something called the right-hand rule. And if you place your right hand in the plane of this page, the fingers of your right hand represent the magnetic field. Thumb represents the velocity, and your palm will represent the force. So let's just do that, an example of that. So if you just pretend, or you can just put your hand on your own paper after you've drawn this, your fingers will be pointing inside of the board or the paper. Your thumb should be pointing to the right because that represents the velocity. Your palm is going to be facing up if you do this correctly. So can you guys see that? Your palm is facing up, so therefore the direction of the magnetic force will be up the plane of this page. And shown that the magnetic force is perpendicular to both the field and the velocity. So let's say in this configuration, let's say the magnetic force will be in the z direction. Your magnetic, let's say your magnetic field will be in the y direction, and then the velocity is along the x-axis. So we have x, y, z. It's three-dimensional. But if you can't visualize this, just note that all of these vectors, magnetic force, velocity, and the field are all perpendicular to each other. So they form a three-dimensional picture. So let's say I'm just taking this picture right here and just tilting it, like turning it a little bit. And so this would represent, the x-axis would represent the velocity. The y-axis would represent the magnetic field, the x's, and then the magnetic force would be the z-axis. So that's basically what's going on. So I have magnetic force along the z-axis, velocity here, and the magnetic field will be going into the plane. So it's really, technically it looks something like this. B, FB, and then velocity like that. So either way, no matter what, it's still three-dimensional. All these vectors are perpendicular to each other. Okay, so step one about the proportionality, or the relationship between magnetic force, magnetic field, and velocity. They're all perpendicular. The first thing I want to say is that the magnetic force is proportional to both B and V. Secondly, if in some case, if the velocity of the particle, this charged particle, as they say, it's a proton. Again, our convention is going all the way back to 23. We're looking at everything in terms of moving positive charges. If the velocity of that proton, and that's our right-hand rule, is going to be with respect to a positive charge. So there is no quote left-hand rule, but if we can find so in this case, the magnetic force is going to be perpendicular and pointing up the z-axis for a proton or a positive charge. And for a negative charge, this magnetic force will be the opposite, because opposite charge. So everything is opposite direction. If the velocity is parallel to the magnetic field, then there is no magnetic force. They all must be perpendicular. So if you have these two vectors here, because what's happening here, we'll see the equation in a moment, is that these two vectors are going to cross. They're going to form a cross product, curl into each other. The velocity vector and the magnetic field vector will curl or create a cross product, or be crossed into each other to form this magnetic force. So in order for that to happen, all of these vectors must be perpendicular, but specifically the velocity and the magnetic field must be perpendicular. If they're parallel, we don't get a cross product. So if they're parallel to each other, there's no magnetic force. If the velocity is at some angle other than 0, we will get a magnetic force. So it can't be parallel, because this would be a 0 degrees, and even 180. It can't be parallel or anti-parallel. They can't be in the same axis. So if the velocity is at some angle other than 0, or even 180 for that matter, because sine of 180 is 0, there is a magnetic force. Fourthly, the magnetic force, as I mentioned earlier, the magnetic force on a positive charge is opposite that of a negative charge. So in that other case, if the magnetic force, since the magnetic force is on the positive z-axis on a positive charge or a proton, then the magnetic force on an electron will be in the negative z-axis. If in fact we have a magnetic field that goes into the page like this, and we have a velocity at some angle, then the magnetic force will be proportional to the sine component of the velocity, because the sine component of the velocity is going to be perpendicular to this guy. That's going to produce a magnetic force. So in this case, right-hand rule, my velocity, my v sine theta, my thumb is going to be pointing upward. My magnetic field is going to be pointing into the page. My fingers should be pointing in or pointing into the page, and for you, it should be pointing into your paper or whatever. And then the magnetic force will be towards the left. Do you guys see that? Do you see, is your palm pointing to the left? Or you guys still have any questions on how that right-hand rule works? Good, so we have the basics of magnetic force using right-hand rule. Let's continue on. Empirically and experimentally, same, we can quantify the magnetic force from the properties in number 1 by magnetic force is equal to the charge times its velocity, is basically a dot product, if you will, because the charge is moving with speed v, velocity v, crossing into the magnetic field. Now, that's a basic case. In the general case, as we said here in 5, if the velocity is at some arbitrary angle, the magnetic force will be proportional to v sine theta. So the general case will be qv cross v sine theta. All right. And, you know, just for your algebraic perspective, the paradigm that you're in now, we can just say QVB sine theta, because we don't have to worry about the rudiments of the cross product. You know, to really treat this properly, we'd have to put it into like a determinant, a little, not like a little determinant matrix, where we have the vectors I, J, and K, and then we'll have the components of the velocity and the components of the magnetic field, and then we do what is called a determinant to figure out what would be the magnetic force acting on this charge. But that's just kind of like a mathematically rigorous way of producing the magnetic force. But this is our basic idea. And of course, this works for all theta that's not equal to 0. Or 180. Anti-parallel or parallel, we don't get anything. We can't get a cross product if it's not perpendicular. Not equal to 0 in the same axis. Yeah, cosine of 180 minus 1, sine of 180 is 0. Yeah, so. Cosine 0, 1, yeah. Okay, from this result, we can say some things about the relationship of the electric field and magnetic fields, electric fields relationship to charges, and, you know, kind of see, yeah, just how they relate. You know, what's going on with both electric field with respect to charges, magnetic field with respect to moving charges and magnetic substances. So we already know, first principles, that the electric force vector is going to be parallel to the electric field. So we have E and we have F, right? So, and we know that already from just kind of looking at that. It's proportional to, they're dot products, well, not dot products, but they're in the same axis, point in the same direction, parallel. Whereas the magnetic force is going to be perpendicular to the field. We see that already, you know, from the previous picture. So there's some differences and similarities between the two fields. The electric force acts on moving and non-moving charges. I can have a charge just sitting out, two charges, as a matter of fact, and they're just sitting. They have an electric field, and in that medium, they have a force of attraction through that electric field medium, and they can be pulled towards each other, whether they're moving or not. The magnetic force needs a moving charge always. The electric force does work in displacing charged particle. That should make some sense. We have a particle here in an electric field, experiences an electric force by some particle that's out here. The electric force and displacement in the same direction as work that's going to be produced. F delta x. So it's parallel. Even anti-parallel, we can have friction or some sort of retarding force that's producing work. But the magnetic force, BF, does no work on the charge because the magnetic force is not in the same plane as the velocity. AKA, well, same difference, if we will, at the displacement, because the displacement vector will be the same plane, the same axis as the velocity vector. So the magnetic force, so you're basically saying the same thing. So the magnetic force does no work on the particle. And we're going to see an application of that. So it does no work since the magnetic force is perpendicular to displacement or V. So, because like, okay, again, magnetic field, let's say it's pointing in. We got this guy, so these are all perpendicular to each other. So we'll see in a moment that if a particle comes into this field, it's going to move in a circle because the magnetic force is going to act on it at all times. It's going to change its direction constantly. So it's going to, produce circular motion of that particle. So we have a centripetal force. The centripetal force will be the magnetic force. So we have magnetic force here. As a particle comes here, the magnetic force does this, and then this, and then this. So cyclotron, we can put a particle in a circular apparatus that's called a cyclotron to produce this effect. Have it spin in a circle for various experiments. So we'll see that. So since there's no work, the magnetic force does not change its kinetic energy. So it's going to be a constant speed. Circular motion, right? So no delta KE, since delta KE equals W, and since no W, no delta KE. By the old work kinetic energy theorem. So there's that on that. Okay. So the units of magnetic field, you guessed it, is the Tesla. 1 Tesla is equal to 1 Newton per Coulomb meter per second, because this is force divided by charge times velocity. Force QVB, magnetic field, that would be F over QV. That's Newton per Coulomb meter per second. We call a Tesla. Nikola Tesla. Since Coulomb per second, we know from last chapter 28, Coulomb per second is 1 amp for current. We have 1 Tesla is equal to 1 Newton per amp meter. So either or. You can also express the units of magnetic field, the Tesla, in terms of Gauss. In a Gaussian units is 1 Tesla is 10 to the 4th Gauss, G for Gauss. And we have different strengths. If you're looking in your textbook on page 6 or 812, different magnetic field strength. MRI unit 1.5 Teslas, which is much stronger than the Earth's magnetic field, so forth. And we want a strong magnetic field so we can get proper readout of what's going on in your body. So we need to have a strong field so we can produce some good images. Strong conventional laboratory magnet, 2 Teslas. Strong superconducting lab magnet, 30 Teslas. The extreme. Plane 9.2, motion of a particle in a magnetic field. So I was saying before, let's say that we have our typical magnetic field going in. I'll do some other examples where it's going out and stuff. So let me close this guy off. This particle's coming in, moseying along, then all of a sudden it experiences a force constantly. It's going to move in a circle. So we have magnetic force is going to the center of the circle at all times. Circular motion, cyclotron activity, or place a field in a circular apparatus called a cyclotron. We're going to get this particle moving, moving in a circle. So those are all my FB arrows. My velocity around the circle, constant velocity, because remember the magnetic force does no work on it, so it's going to keep it in the circle but at a constant speed. So that is velocity, and of course these are my field lines. Questions? That was black. Now, the centripetal force in this case, the centripetal force in this case is equal to the magnetic force, which is equal to mv squared over r. Or the centripetal force is equal to this. Centripetal force is equal to this. But what is the force that makes up mv squared over r? Well, it's the magnetic force QVB equals mv squared over r. And if we want to find something like, say, the cyclotron radius for a particular magnetic field at a particular velocity for a particular particle, like a proton, which is 1.67 times 10 to the minus 27 kilograms. So all those things being constant, how large do I have to build my cyclotron for a particular field, for a particular speed, for a particular mass? I know the charge of a proton. Well, oops, I can figure that out. This one goes away. So that's going to be, so the cyclotron radius, or the cyclotron has to be built with this radius, which is equal to mv over qb. That's what's called your cyclotron radius. Berkeley has a cyclotron. I went up there once, pretty big deal. It's large. You know, performing experiments, you're smashing particles into each other at particular magnetic fields, and you're trying to get up to the speed of light. So your radius is going to be, you know, proportional to the speed of light. So it's going to be a huge apparatus, and it's pretty big mass and all that good stuff. So yeah, as we can see, proportionality, trying to get speed of light. Well, this has got to be huge. The radius must be large for these protons, this particular charge, and for a particular magnetic field. The magnetic field's appreciably small, and this is appreciably great, you know, for this large radius. And you can tweak the magnetic field. There's all kinds of dials and computers and instruments all over the place where you can modify the fields and sort of stuff in order to get what you need. So to get you what you need. All right, so this was typically called the cyclotron radius. And we also know from a tangential velocity of a particle or mass around a circle is equal to r omega. If I want to find the angular frequency, which is v over r, then I know that, you know, r is equal to mv over qb. Then my angular frequency of this particle moving in a circle in a magnetic field is qb over m. This is what is known as my cyclotron frequency. Protons are a particular charge with a magnetic field and they have particular mass will always have this frequency. I want to increase the frequency, increase the field. Send you in faster, more frequent. Now you just, at this point, you're just playing around with physics. Okay, now I want to figure out the period of this particle in the cyclotron. So I'll do 2 pi r over v. Know that from circular motion stuff. And then write it up again here because r over v will be 1 over omega. So it'd be 2 pi over omega. And I know omega is this. So therefore, my period in terms of the mass of the particle and magnetic field will be 2 pi m over qb. Different ways of expressing the same thing. Mass of proton, charge of proton, magnetic field in question. I want to increase the period, reduce the field. Reduce the period, increase the field. And that's contiguous with the angular frequency. And I can, you know, the actual frequency, if you're looking at it in terms of wave perspective, f, you know, omega is equal to 2 pi f, well then f will be omega over 2 pi. So same really. It'd be qb over 2 pi m. So it's just the inverse of this, yeah. Because, you know, frequency is 1 over period. And Questions? Omega, yeah, I just said that as a cyclotron frequency. Particles circulate. This frequency in a cyclotron, So that's why it's called that. That. So this is pretty, yeah, it's basic physics. Circular motion physics. Now you're doing a magnetic field, guys. All good?
Yeah.
Yeah. Tell me what the question is. That didn't sound convincing.
Well, I was
Okay.
uh, I'm thinking about this uh, uh, if it's a circular motion,
Yeah.
like if we have just two particles there, uh, where there will be just a linear motion in
Well,
that magnetic field.
we can do linear at some other point, but the point is what's happening if I have a particle moving in a field like this, then we just deal with that right now. But yeah,
And if we have a circular motion, it means the uh, there are two particles that have strong charge that are kind of
no, 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 no,
have
no, no,
the
no.
role of poles, right?
Mm-mm, mm-mm. No, circular motion is you have one charge, you don't have to deal with two or more. And it's coming into a field in this configuration. You're going to get a particle moving in a circle because of how the magnetic force is going to act on this particle. It's going to act as soon as it comes into this field, the magnetic force will be perpendicular to that velocity at all points. It's going to keep
Yeah,
acting.
yeah. I was talking about the force source, the source of the force that it has to be charged, right? That will affect
It
on
has to be
other
a moving
particles.
charge. It has to be a moving
Yeah,
charge.
yeah, yeah.
Yeah, because static charges won't produce a field or a force. Magnetic force.
Yeah.
Mm-hmm. Now, I was trying to get this picture. You can see the picture in your book, but I'm trying to visualize it so I could um, uh, draw it. But if we have a charged particle moving at some angle with respect to this field, it's going to move down the field in a helix, like a helical pattern. DNA, because we need two, but it's going to be a helix at some angle with respect to. But you have a visual in your text there, kind of sort of gives you a visual there. Moving at some angle. Respect to B. So, trying to visualize this. So I have, there's my y-axis, z, and then my x. So my magnetic field is going to be through the YZ plane. So it's going to have like magnetic field lines like this. You can imagine this is the origin. It's like coming from another dimension through the YZ plane. Not literally. Okay, so it's like the plane. And here's the x-axis. So try to visualize this. This blue line. So maybe I should have done this. Give me a second. I'm gonna have to run a cough. Resume recording. Okay, so if I have my velocity kind of pointing up like this, I have a component that comes all the way down. This would be my y component because y-axis, and then this here will be like the shadow of this guy. But then, so this particle comes at a velocity at some angle with respect to the field. So the field is going to be, linear like this, but this blue line is going to be like off axis or at some angle. So the magnetic force will be pointing to the right in this case, if you use right hand rule. So I'm going to start the magnetic force right here and point all the way over, point like that. So it's going to pull it's going to change the direction of the y-axis and z-axis will be here. It's gonna change the directions. It's gonna change the size and it's gonna change the magnitude of both the y velocity and the z velocity. This one's gonna get shorter. This is gonna just change direction. So there is a change only along the y and z axes. So if anybody was along the x-axis, it would see this coming down as in a circle. But you know, when you look at the entire picture, it's this particle is going to be moving in a helix, a helical pattern. It's going to something like that, all the way down. But the x-axis person just sees circles. That's kind of the picture there. So velocity at some angle theta with respect to this, to these two lines. You kind of see that, or really see it? So
yeah, kind of.
yeah, it's kind of, you know, better visual in the text, but I was just trying to draw it.
Is it in the book, Mr. Kelly?
I kept saying, is this in the text? Yeah, it's on page 814.
Okay.
Yeah, try to follow along text and notes and all that. So it's the y and z components that change, but the x-axis doesn't. But long story short, you have a particle moving at some angle in a field. It's going to be a helix, kind of like a winding. A winding that's kind of off axis, a helix, helical pattern. So,
Mr. Kelly,
yes.
can I ask a question?
Yeah.
But what causes it to have that helical pattern?
The velocity is off axis. It's not in this. It's not exactly perpendicular to the magnetic field. So when it's not perpendicular,
So it's at a certain angle.
At a certain angle, at some angle other than 90, it's going to now have a helical shape down the x-axis.
Oh, okay.
Yeah. So there's no acceleration along the x-axis, but there's acceleration along the y and z axes. And you can find the total velocity vector by doing a Pythagorean sum along the y and z. And that particular velocity will be perpendicular to the magnetic force that's produced in this pattern. In other words, before I write the applications, the total velocity vector is going to be Pythagorean, not x, Pythagorean sum of the y and the z axes, and this velocity vector is perpendicular to this FB, and that's, now you got all your perpendicular stuff. Okay, FB perpendicular to velocity, perpendicular to field. Good. So that is going to give you that helix pattern. Okay, let's say that you have a charge moving with velocity v in the presence of electric and magnetic fields. The force that this particle feels is called the Lorentz force. So FL, if I may, it's going to be QE plus QVB. It's going to experience an electric force and a magnetic force simultaneously. because we have two fields. What if we want to, we're trying to perform some experiments and we wanted the particles to have the same velocity, or constant velocity, but and also we didn't want the particle to be deflected in any way, didn't want to go in a circle, we didn't want to go into a helical pattern. Well, there's something we can do is create what is known as a velocity selector, and I will show that in a moment. So let's say we have a charged particles to move at same velocity. Well, place charged particle in a combo E and B field. Well, something that looks, we could, put this charged particle in what is known as a velocity selector. So let's say that we have these two plates, or whatever these conductors are, at opposite polarity, and then we have a magnetic field that's pointing into the page yet again, and we have a particle going through the center of this field, or within the field. Well, we know that there's going to be, so the particle does this. Yeah, that particle is moving up. We know that there's going to be an electric field that's pointing to the right, because electric fields go from positive to negative. And by the right-hand rule, the magnetic force will be pointing to the left. So, because like your thumb should be pointing up the plane, and your fingers should be into the board or your paper, and your palm points left. So we have a magnetic force that points like this. Once these two are equal, this guy is going to be moving at the same, or at constant speed when the forces are balanced. Newton's first law, right? So the magnetic force is equal to the electric force. QVB equals QE. And then the velocity will be given as electric force divided by electric field divided by magnetic field. And those particles will always have the same V at those E and B, E and B fields. And thus no deflections or circular motion or anything. So it's going to be going straight. Stanford has what is known as the Stanford Linear Accelerator Collider. And I believe it uses this principle of the velocity selector, because they're accelerating particles along a straight line. Whereas at Berkeley, they have the cyclotron. So it's just choice, money, preference, all that stuff. Another application is the mass spectrometer. It is a device that allows you, the experimenter, to determine what kind of particle is coming in to your experiment, or to your, like you're trying to determine what kind of particles are being accelerated, and you're accelerating some ions in, and you want to see which ones are positive or negative. What kind of mass do they have? So we can select those or separate those out in what is known as a mass spectrometer. So generally ions, because we were looking at charges. So we're going to separate ions according to mass charge ratio. So that device looks something like this. Is a typical look of, well, example look of a mass spectrometer. So we have a magnetic field here. Let's say we have this, and then we have, and we'll just call that magnetic field not, or original magnetic field. Doesn't matter because we have, and then the particles coming into a magnetic field region through this linear portion. So as it comes in, this is like a combo, looks like a combo velocity selector and this new guy here. So this guy's coming up, and then if it's a positive charge, it's going to get deflected to the right. If it's negative, and so we can kind of look at what kind of ions are coming in. We can determine the masses, all this good stuff. So if the particle is negative, it gets deflected right, and positive deflected left. And you can determine that by right-hand rule. Fingers into the board. Velocity vector is up the page. Your palm is to the left for the positive charge. And so it's opposite for negative. Now, in this top region, we can determine this mass charge ratio business. By this. So we know up here is going to be a semicircle, but it's basically a circular circular motion that's being produced here. And so the magnetic force is a centripetal force. And so we have mv squared over r equals, I keep that consistent here. So we have mv squared over r equals q times b, no electric field in question there. And QVB, so that goes away. Then I want to get this mass charge ratio business, so m divided by q VR equals b, so m over q is going to be RB divided by velocity. So this relationship here, depending on the radius of deflection and the magnetic field, call it B naught, keep it consistent, divided by the speed of the particle, we can figure out what this ratio is. And then from that, we can, figure out the mass of that particular ion, and so forth. If the particle had, if it was in a velocity selector and where we had an electric field, we know from the previous equation that the velocity is equal to electric field over magnetic field. And so if there's a electric field in this portion as it gets deflected up top, left, let's say, it's a magnetic field and electric field. Then we can just substitute this guy in this equation and get a new expression that involves the electric field. So instead of m over q equals RB naught over V, we have m over q R B naught B over E, because it's 1 over V. V is this, flip it over, and we have that. So this would be mass charge ratio for both fields, and that's just for the magnetic field. Mass spectrometry is just very good at identifying different ions, their masses, definitely something that was part of early experiments in determining what kind of reactions could produce lithium in stars. Mass spectrometry. You send a proton in and you get a bunch of stuff scattering all over the place, and you can figure out, okay, you can figure out scattering parameters, like how close the proton comes to these ions, what kind of ions are involved, carbon, nitrogen, oxygen, ions. Many different varieties of experiments you can use to determine what's going on in those types of experiments. So mass spectrometry, very, very useful in figuring stuff out, figuring out what kind of ions you're working with. So, J.J. Thomson in determined a mass charge ratio of electrons, and he used a similar technique of this mass spectrometer back in the late 1800s. So yeah, a lot of good applications here. All right, bloviate on that. Move along. Okay, so let's say we have a cyclotron particle spinning around and we want to, shoot it out. Can we determine the kinetic energy? We can. Kinetic energy of particle as it exits the cyclotron. So we know from the cyclotron radius, that formula, QB, we can figure out the speed. So V is going to be equal to Q BR over M. You just do a little algebra, multiply this over here, QBR divided by M. Then you also know that kinetic energy is 1/2 mv squared. So the kinetic energy of a particle as it exits a cyclotron, you substitute V for this, is going to be Q squared B squared R squared over 2M. Right? Questions on that? You can see it's a bunch of math derivations of this algebra. So we just took this and made it squared. So this is going to be M squared, and this M up top, this goes away. All right. So I think the last thing in this chapter, we're going to look at magnetic forces on wires. Just real quick there. So the magnetic force on a current carrying wire is given as the current times the length of the wire, and its cross product with the magnetic field. Very similar to Q V cross B, because this is just one charge with a speed. Now you have multiple charges with their speeds. It's going to create current over a length of wire. This is a very similar dynamic. And then we get a magnetic force. So let's say, for example, now I'm going to give you a test. So I have a magnetic field that's pointing out of the page. There's dots, like arrow heads coming at you. And let's say I have a current carrying wire So we have a wire that's, this would be the direction of the current inside of the wire. Where does the force point? Anybody?
Perpendicular.
Yeah, so magnetic force points right, because your finger should point out. So let me just specify, be clear. So again, same, right hand rule. Fingers represent the field. Your thumb, now in this case, it's the current, which is up. Your thumb should be pointing up. Your palm is the force. So fingers out of this board as if a bunch of arrows are coming at you, at your face. Thumb pointing up, and your palm should be facing right. And that's why the magnetic force is to the right. And you guys see that?
Yeah.
Okay. Yeah. Okay. All right. Yeah, I mean, I just cut out the middleman and how they came with the current. We did a microscopic viewpoint of what current is. That goes back to chapter 28, first part. So it's just a bunch of charges moving moving through this wire, produces a current. That current takes the place of velocity of one charge. Now it's velocity of many charges. To produce the current, I times L cross B, cross product produces a magnetic force, and there we go. And then we can do some integration on this if we add little pieces of wire, DS's, but I'm not going to do that here for time. So like I said, we're going to skip the torque section and the Hall effect. Please read that if you're interested. It's very good stuff. We're going to push on to chapter 30, chapter 30.2. Let's flip over there. Okay, and in this chapter, we're talking about sources of the magnetic field. So we're going to look at magnetic forces between two current carrying wires, talk about Ampere's law, talk about Gauss's law for magnetism, magnetic field of a solenoid, and that's where we'll stop. Just very basics. So just want to just touch and not dive too far into the weeds, or we'll run out of time. Okay. I did this experiment one time at the other school I taught at, the magnetic force on current carrying wires. We got, got it to work. It was nice, but it was very hard to see. We had to get up close because my generator was very weak, my battery. So I couldn't produce enough current to produce a large enough force. But we got it. Magnetic force. Between two wires. Nitty gritty. You have two wires with current in the same direction. The wires will be attracted to each other. Opposite directions, they're going to repel. And so a quick picture of that, you can see at the top of 843. So for example, let's say that this is wire 1, wire 2. The magnetic field from wire 2 is going to wrap around 1. And since we have the current in 1, before going back to the right-hand rule, the current in 1, your thumb's going to be pointing to the right, and magnetic field is going to be circular. It's going to be kind of doing something like this around 1. Okay, and if I'm interested in the force of 2 on 1, Well, the force of 2 and 1 is going to come down like this. And then this, this, different color. The green is your field, your magnetic field. And so, as we know, those guys are perpendicular to each other. They're all 3 perpendicular. So this black arrow is the current. It's perpendicular to the force and the field. And so 2 current carrying wires, current in the same direction, will be attractive. And then opposite directions repulsive. So if we were to make this empirical, the force the force on wire 1 is going to be equal to the current in wire 1 times the length, I mean, it's the same length, and produced by the magnetic field from wire 2. So that is, you'll see that this is 2, and the L's are the same, and this will be I1 and I2. Well, in the previous section, and even as we go ahead for Ampere's law, the magnetic field from wire 2 is given as mu naught I2 divided by the circumference of this field. So it's just 2 pi and then give a radius a. So 2 pi a or 2 pi r, where r is equal to a, arbitrary variable. So now we place this in here and we get I1L mu naught I2 and 2 pi a. And we got the same thing from F for F2, same magnitude, different expressions. This is going to be I2, this is I1, 2 pi a, L is the same. So same magnitude, they're going to attract. And opposite directions, they will repel. So, so this will be I1, I2, mu naught L, or 2 pi a. And conversely for F2, it would be same thing, really. Multiplication. Do you have an appreciation for that? Do you see that, what I'm saying there?
Yeah.
Because now, I mean, it's just the configuration, but we can choose anything we want. I want to figure out what is the force on 1. Okay, well, wire 2 throws out a field, circles around 1. Its field is going to, at this point, going to be perpendicular to this current. Magnetic force is going to be pointing down. It's going to be attractive. Currents, same direction. Attractive. Currents, opposite direction, repulsive. And we got in our lab, we got the attractive, barely, but we saw something. Everybody, all the kids confirmed. Yay! That was a while ago. Okay, so messing around with the formula, but moving ahead, I've also done this little trick too. Ampere's law. This is pretty cool because I used to, when I was teaching AdvPhysics B, and you had to teach everything, mechanics and electromagnetism. I had a piece of cardboard with a current carrying wire through the middle of it, and I had some and I had compasses around the wire. They were all pointing in one particular direction for the current going up, and then I reversed the current and they would point the opposite direction. So boom, verification of Ampere's law. Very similar to the picture on page 845. So basically for Ampere's law, the if I have a wire and some sort of apparatus around it, then I'm going to get a magnetic field that circles it, like in this direction. Okay, it's going to be concentric circles because field lines are going to, and way out here, the magnetic field will be very weak or whatever because it's very far away from the wire. So if we point our fingers up, your right hand rule, your current represented by your thumb, then your fingers are naturally going to curl, in a counterclockwise direction. You guys see that? That's why my circle is like this. Counterclockwise. Yes, no?
Yeah. Yeah.
Yeah.
Okay. So or you can just imagine this current coming out of the page. Your thumb comes at you. Your fingers are going to go counterclockwise. Is that better? Your fingers should be wrapping around like this. And this is just kind of like the vertical picture. Then if your current was going into the page, it would be clockwise.
Yeah, I got it.
So Ampere's law is just the relationship of the magnetic field is going to be equal to this proportionality constant, mu naught, permeability of free space, mu naught I over 2 pi r. Now, the further away you get, the magnetic field is going to drop. Basically, go to 0 for said current. That's the long and short of Ampere's law. I'll cut out the details. So that's the basics. Now I'm going to go to 2 more sections. Magnetic field of the solenoid. Wait for this thing. So solenoid is like, if you ever seen in my class, these little cylindrical devices that have wires around them. And so we were just trying to figure out, so I'll just do it from the side view. And so if I have current wrapping around like this, little copper wires, so this would be a solenoid. So we're trying to figure out what is the value of the field going through this solenoid. So you can have many of these lines. So why do I draw that? Because if I have my current going up and around, like going up and over through these wires, let me just try and draw a bigger picture here. Going up and then down, up like this. Then by right hand rule, now my fingers are going to be the current. My right hand, my right hand rule, my thumb is going to have magnetic field moving in this direction. My thumb is going to be pointing left, wrapping around. And that's why I get this picture up top. This picture. And then, you know, n number of field lines. Well, this magnetic field through the solenoid basically going to be determined by this equation here, mu naught n over L times I, where I is current. So n represents the number of turns in a solenoid. Have you guys seen my solenoids? You know what I'm talking about? Those little cylindrical things with wires around them? You guys remember those?
No, I haven't seen.
You've seen them before. It's been a long time. Yeah, but they're
Maybe I
basically,
don't remember.
yeah, they're, if
Yeah, they're
you,
orange and they like coil.
yeah, they got the coils around them like the copper wire. So they're, I mean, see me do a vertical. So I have, you know, they're kind of like this. I got wires all around them like that. Very, you know, tighter than that. But so here is an entrance exit, you know, sitting on the table. So n represents the number of wire turns. Over this length, right? For length of wire. And so we'll then, you know, we can simplify this and say, okay, well, n represents n over L, just to kind of simplify the, you know, fraction, which is number of turns per length. So the magnetic field that's coming through this solenoid is basically mu naught n I. Kind of similar to the magnetic field of current, but we just don't have, you know, a circumference dependence. And the basic reason for that, at least physically speaking, visually speaking, is, well, the magnetic field is going through the solenoid. It's not increasing or decreasing around a current. This time, the magnetic field is, well, linear, as opposed to the current. The current is going on a coil this time. But we're interested in finding out what the magnetic field will be in the solenoid, and this is our equation. So let me explain these variables. It goes back to the previous equation. This is magnetic field, mu naught permeability of free space. Verify that. Yep. Yet another constant. No. Okay, and that's equal to 4 pi times 10 to the minus 7 Tesla meters per amp. N is this number of turns per length, and I is your current. Increase the current, the field gets really intense. And when I have done, I could probably just show you next time, a little time beforehand. I have created a mock power station in class, and I put a whole bunch of bar magnets inside of these solenoids to create, you know, a mock transformer to induce voltage. And the more magnets, the more current, vice versa. So we can kind of see that from this formula. Okay. Last thing is Gauss's law through matter. Gauss's law and magnetism. Very similar to Gauss's law for electric fields. That's our last topic. Sheet of paper, substance, some plane of
area.
Yeah, some area of the. I'm trying to think of the terms. Just something. Some material. There's my word. Some material for this magnetic field to go through. Well, these are field lines. Again, the area. This area vector is going to be the same direction as you. So this is your normal vector. So basically, the normal vector just kind of represents each piece of area, if you will, at the point of contact or the point at which the magnetic field goes through. So we can call this N or dA, you know. Well, then the magnetic flux through this piece of material is going to be given as B dot dA. This is a dot product. They're moving parallel to each other. And if the magnetic field was at some angle, we would look at the cosine component of dA. So this comes out to be BA. You know, that's a basic equation, but if magnetic field was at some arbitrary angle, we look at the cosine component. So the general equation that's a theta equals 0 or 180 is some arbitrary angle. And if theta is equal to 0, it's just BA. Well, at 180, this would be negative BA. That means that, okay, magnetic field's going this way. It's just orientation. My first orientation was to the right, and if I switch it around, well, then my area component is to the right as my field goes left. And so my magnetic flux will be negative BA. You guys see that? Because cosine of 180 is -1.
Oh, yeah.
Mm-hmm. Get these spam calls. Okay. Units of magnetic flux. I like this. It's the Weber after this guy Weber. One Weber WB equals 1 Tesla meter squared, because magnetic field times area. Weber's. That's the basics. You know, if you want to read up on the Bohr magneton, magnetic moments, that's 30.6. Probably next time I'll touch on different types of magnetism, because those are very important to understand. Ferromagnetism, paramagnetism, and diamagnetism. Before we go on to Faraday's law of induction.